Hello, this is Mr. Mac. This is a video on the concept of continuity. Now, continuity intuitively means that if you start at some point and you draw a curve with your pen or pencil to another point and don't pick your pencil up, that those 2 points are connected by that line. And if you look at the word continuity, it contains continuous. So in other words, a continuous line is connected, and that's the whole idea behind continuity. Now, to actually define continuity, what we're going to say is that f of x is continuous at a if and only if the limit as x approaches a of f of x is equal to f of a. Now, if you think about this, what we're saying, let's put an xy axis on this, and we'll let this be f right here, and let's let this be the point A. See, this value would be f of a, and as we approach a from each side, if the value of the function is approaching f of a, then we know the limit as x approaches a of f of x is equal to f of a, or is equal to this value here, but we were calling it L before because what we had sometimes was things like an open circle here with a point up there. So what we're saying is if the value that we're approaching as a limit is the same as the defined value for the function, in other words, if this point is actually here, then the f is considered to be continuous at a. Now, if you look at this definition, Stewart has some things that he says here. He says, number one, it has to be the case that a is in the domain of f. Now, you see that over here because when he says it's equal to f of a, that means f of a exists. It has to be true that the limit exists also. So in other words, this side is actually equal to something, and then it has to be true that this is equal to that. It seems to me, I don't know for sure, but it seems to me that this statement by itself would be enough rather than splitting it up into 3 different things. But we would make mention of the fact that a is in the domain of f and the limit exists. But that one statement there should be sufficient to tell that. And the concept of this is that the function, if it's continuous at a point, it is connected to the points next to it, although mathematically we don't know what point is really next to it. Let's not get into that. This is the way we handle that. Now, we also need to realize that if we have, like say, a closed interval, let's call this function g, and we'll put an xy axis on it, and let's let this be g of a, and this point right here can be g of b, and that would make this a and would make this b. We would say that the point g of a is continuous from the right. In other words, it may not be, it's an endpoint. It may not be defined to the left, but it continues from the right if the limit as x approaches a from the right of g of a, of g of x is equal to g of a. And we would say that g of a is continuous, or g of b is continuous from the left if the limit as x approaches b from the left of g of x is equal to g of b. So in other words, we can have left-handed and right-handed continuity of endpoints. take a look in the book on that and consider it a little bit. I think that you won't have any trouble with that. Now, the next thing that we want to handle is, little operation things with limit. Now, if we have the limit as x approaches a, g of x is equal to L, and the limit as x approaches a of f of x is equal to, let's use m, then the limit as x approaches a of g of x, and we're going to have an operation symbol here, f of x, and see we put this in here, is equal to, now I'm going to put L and m out here. Now we can put a plus sign in here and a plus sign there, or we can put a minus sign in here and a minus sign there. In other words, the limit of the sum of two functions, or difference of two functions, is the sum of the difference of the limits. So we can have, minus signs in there. We can put a times sign in here, and that would go here. Now, we can also put a division sign in here, but we do have to put one additional proviso over here. That's provided the limit as x approaches a, that should be an a there, of f of x in this case is not equal to 0. See, in other words, we can divide these limits as long as the limit of the denominator function is not 0. And then also, of course, since now, if the limits of these, okay, now if L is equal to g of x and m is equal to f of x, then continuity works for all of these things too. And then, of course, you can multiply by a constant. That doesn't change anything either. All right, now, we get to a couple of things that really need to be said. Okay, now, it turns out that the following functions, polynomial, rational, what else have we got? Root functions, trigonometric functions, inverse trig functions, logarithmic functions, and exponential functions are all continuous on their domains. In other words, if you have a rational function, you know that any value that makes the denominator 0 is not in the domain, so it's not continuous there. But if the input value is in the domain, then those functions are continuous on those domains. All right, now, you also can do continuity with composition of functions. I'll let you take a look at that in the book. It maybe is kind of complicated and dry to state it, but it's not really difficult to follow. So I'll let you do that. And then, if you have questions, you can ask them in class. Now, the next thing we get to, and the real big reason for continuity, is so that we can handle the I, V, T. Ta-da! Okay, now IVT stands for intermediate value theorem. And this one is so important that most people understand what you're saying when you just say IVT, intermediate value theorem. Now let's see if we can talk about this. Okay, so first of all, if f is continuous on a closed interval from a to b, and f of a is not equal to f of b, then if any number, let's call it n, capital N, is in the interval from f of a to open interval from f of a to f of b. Actually, it doesn't need to be open, it can be closed here. If any interval is, if any number is in the closed interval from f of a to, no, it has to be open, I'm sorry. Excuse me on that. If any number is between f of a and f of b, in other words, it's on the open interval between f of a and f of b, there must exist a c so that f of c is equal to n. You look at that and you say, gee, great, put it outside. Let's take a look at a picture of what this is really saying. This will probably help a lot. Okay, now what we've got is we've got a function that is continuous on the closed interval from a to b. So what I'll do here is I'm going to start out and put a point here and a point here. Now, this would be f of a, and this would be f of b. And let's let this function just kind of go like that. Now, if we choose a value n in the interval between f of a and f of b, then there must exist a c on the interval from open interval from a to b so that f of that value will give us n. Okay, so here's what we do. We look back, we go over here, and then down here. So this is c, and it turns out then that n is equal to f of c. Now, we're assured that for every value in this range, there is a value in this interval right here that'll map to it if f is a continuous function on the interval from a to b. Now, that may not seem all that impressive, but think about this. If we know, for example, that we've got a polynomial and p of 1 is -1 and p of 2 is, say, 3, then we know, since they're continuous, since a polynomial is continuous, that there must exist a c somewhere between 1 and 2 so that p of c would be equal to 0. And this is used a lot in finding roots and so forth. There are other strange times when you want to assert the existence of a functional value that gives you a number between two others, and it's the intermediate value theorem that does that. Let me close with this, because I think this is really kind of a neat application of the intermediate value theorem. Okay, you have a monk, and he lives in a monastery at the foot of a mountain. So I'm going to draw a really horrible mountain here. And there's a monastery here at the foot of the mountain. Some kind of religious symbol here, I don't know what. Anyway, so, and you've got a monk that lives down here. Okay, now, on Saturday at 9 o'clock, the monk climbs up the mountain to a shrine at the top of the mountain. So he climbs up the mountain to the shrine, and he spends until 9 a.m. on Sunday up at the shrine meditating. Okay, now it's Sunday at 9 a.m. The monk heads back down the hill to his monastery where he lives. Okay, now while he's coming down, he stops and rests on a rock. So he's sitting here on a rock resting. And it occurs to him that he's at the exact same height that he was yesterday at the exact same time. Now, is that just a coincidence, or does that have to happen sometime during the trip? Okay, spoiler alert here. If you want to think about this for yourself, now's the time to hit the pause button. Okay, have you thought about it? Let's look at this. If we put a graph, and on the graph, the horizontal axis will be time of day. And in the vertical axis, we will have distance from the monastery. Now that's the building at the base. I don't know if I spelled monastery right. I'm not even sure what letters I used there. But anyway, here we go. So we've got a distance. This is where the shrine is, and this is where the monastery is. Okay, so, and we'll have 9, 10, 11, 12, ... 1, 2, whatever we need. Okay. Now, so Saturday, the monk leaves the monastery at 9 and he climbs the mountain until he gets to the shrine. Okay? Sometimes he goes faster, sometimes slower. Here, maybe he slipped a little bit and slid back down. Anyway. But he's continuously somewhere on the mountain, so his distance from the monastery is a connected function. Now, the next day at 9, at Sunday at 9, he decides to go back down, and he probably goes down faster, but again, his distance is connected. Now, this point right here is a value of distance from the monastery and time of the day, and where those two graphs cross, that monk must be the same distance from the monastery at the same time. So in other words, this is something that has to occur by the intermediate value theorem. All right. I'm going to end this video now with the, and we're done.